we are having the four types of power amplifiers. Those are Class A power amplifier, Class B, Class AB, and Class C power amplifiers. So among those, we are going to discuss the three types of power amplifiers according to our syllabus. So first, let us see the Class A power amplifier. Class A power amplifier. So I'm going to explain step by step what is the power amplifier, especially Class A power amplifier. After that, we're going to discuss already we discussed one power amplifier, so we're going to discuss remaining power amplifiers within less time. So please be concentrated on this topic. So you can see on the screen, you can observe that. So here we're having the cell bias circuit, and we're having cell bias circuit. This is our base RB resistor, and this is the NPN transistor. NPN transistor, and you need to give me one that this transistor is a, let me show it the key. This is a transistor, right? So in this diagram, the second unit we have taken every transistor is normal transistors. Now here we are going to take power transistors. I told you already in the last class, we are going to take the power transistors in designing the power amplifiers, right? Why? Because we are going to analyze the low signal, low signals, right? So for that we need more power. So we are going for the power transistors, and here we are using this T is the power transistor, and we are having the base resistor as well as the RC collector resistor. This is the input voltage, and we are going to take output at this node, and the voltage between the collector and emitter is what? VCE voltage, VCE voltage. And if we talk about at the operating point, that is the DC load line, we take is VCEQ, right? So that's not other matter. There is a circuit diagram for the Class A power amplifier. You may have the different circuits also. Don't worry. If you are searching in the textbooks, you will have one more resistor under this base. So does not matter. So please be concentrated here. I hope you are getting me. Let's go for the DC analysis. So here I told you already, we have divided the power amplifiers based on what? The position of the Q band. That we have seen already. The position on the Q band, we have divided the power amplifiers. Those are, if the Q band is in the middle of the DC load line, then we can say that the corresponding power amplifier is a Class A power amplifier. Now let us see the thing. So I'm drawing the this load line diagram. So for that, what we require, the requirement is what? We require the output characteristics, of the transistor, as well as the what? We require the DC load line. We require the DC load line. Okay. So on the x-axis, we are actually going to take collector current, IC, collector current, IC current. On the y-axis, we are going to take VCC, the output voltage, VCE output voltage, and we are going to make IC value 0 and we'll find out the output voltage, and we'll keep this point here, as well as we'll make VC voltage 0, and we'll find out one point on the y-axis, that is this point, and the line joining these 2 points is called as which line? This is the DC load line, right? It was discussed while we are discussing the transistors DC load line. Now after that, we are going to draw the output characteristics, and you know the output characteristics of the transistor will be, you have already seen like that. It's like a parabola. This is the output characteristics of the transistor. Padma Pujita garu.
ఒక్క నిమిషం అక్కన్న ఇదేంటో స్పీకర్ అది
Please mute yourself. Okay. So we know that what this one is. This is the DC load line, right? This is the DC load line, and this one is what? This one is the output characteristics of transistor. Output characteristics of transistor, and this point is called as what? The intersection of the output characteristics and the DC load line is what? It's called as a Q point or operating point, or we call quiescent point. And this is given by what? The VCEQ, is y-axis point, and x-axis point as well as the y-axis point ICQ. Okay, so this point is known as the ICQ. This point is known as the ICQ, and this point is known as the VCEQ. And you can observe that I have drawn this Q point in the middle of the DC load line. I have taken this point is on the middle of the DC load line because we are talking about the class program amplifier, and we are going to check whether this Q point is on the middle of the DC load line or not. So with that, we'll do that. This one is the IC maximum value. This is the VCE maximum value. So I'm going to verify that whether we are getting the complete cycle of the input, the output or not. So here we are given what? Q point is on the middle of the DC load line. Please observe here. This is my input voltage. Input voltage. Please treat it like sine waveform. This is sine waveform. Please treat like sine waveform. Of course, it's not looking like sine waveform, but treat it like sine waveform. This is the 0 volts. Sine waveform 0 volts, and V minimum voltage. And you know that for sine waveform we are having the minimum voltage and maximum voltage and peak to peak voltage like that, right? We take time period. This is a T. This is the T. 0 T by 2 T. So here for this input voltage waveform, so this is the 0 time, and this is the T by 2 time. This is the T time. This is the minimum voltage. There is a negative portion. This is the maximum voltage, right? So now in the output section also we are going to get the sine waveform. And here someone is waiting in the lobby. And you can observe here. So here our this point Q point is on what? On the middle of the DC load line. Okay, please keep in mind that while we are discussing the DC analysis, we are going to make that this input voltage capacitor is going to be what open circuit, right? Capacitor is going to be open circuit. Why? Because in the DC analysis frequency is going to be zero, so that the capacitance XC value is going to be infinite. So we can replace with the open circuit here. So here if the Q point is middle on the DC load line, so here the portion whatever this voltage waveform is going to be projected at the output section. If you observe here, so middle means what? This out portion will be covered in this portion, and this out portion will be covered top of this here, right? So complete cycle, the complete cycles will be appearing at the output section. So this is a zero, this is the time t, and this is the I minimum value, and this is the I maximum value. Okay, so now here the main intention is we are getting the complete waveform. That is, we are getting the 360 degrees here. So classic power amplifier is 360 degrees. So there is no clipping. There is no clipping of the waveform here. If you observe here, for example, we are having the this peak to peak voltage. V minimum to V maximum is, for example, we are having amplitude of 10 volts. We are going to get 10 volts. We are going to get the definitely 10 volts. And if you are having the time period is about 10 millisecond, this the output also we are going to get time period is 10 milliseconds, right? So we are getting here complete 360 degrees of waveform. So class A power amplifier is a 360 degrees type amplifiers. Let us see the analysis here. So it is about diagram. Let us see the mathematical analysis. Mathematical analysis. So let's do the DC analysis. As we have drawn the DC load line, so let's do the DC analysis. DC analysis. If I write cable expression at input port, if I write cable expression at the input port, then what are the things are going to be get? What are the equations are going to get here? So take this diagram. This is the VCC voltage. And while we are doing the DC analysis, the capacitor is going to be what open circuit. So then this is the input port. This is the input portion. This portion is the input portion. Now, if you write the expression, cable expression, the input, so what we are having here, which voltage we are having? We are having the VCC voltage. VCC voltage as well as the drop across this RB resistor, as well as this cut-in voltage, VP voltage, right? So we will take this cable expression, and while the current is flowing in this direction, so this top of the RB is going to be positive, bottom of the RB is going to be negative. So if I write that expression here, we are going to get this VCC minus IB RB and minus VBE equal to 0. EB equals 0. From this we can find out the IB current. So IB will be what? IB will be the VCC minus VBE over RB. And this is the what? This is the, I can say, IBQ. That is the base current corresponding to the Q point. Corresponding to the Q point, IBQ. Why? Because we are doing DC analysis. So while we are drawing the DC load line, we are going to get the Q point. So IB is called as the DC load line base current. But we require what? We need the ICQ. We need the ICQ. So you have drawn the DC load line with respect to IC and VCE. So we need the ICQ. And if you know the beta value of any transistor, we can find out what IC. And if you know the IB value as well as the beta value, from that we can find out what IC and beta will be given while the transistor is designed So beta will be given already. You can take here IC, find out IC will be beta times of IBQ. Okay. So it is about IC2 point. That's on the DC low line point. Let us draw the, let's write the KVL at output. KVL at output. So what is the KVL here at the output side? So this is the output. This is the output path. Output path. We can observe which voltage we are having while we are drawing the Kirchhoff voltage law. We are going to face VCC as well as the drop across the RC as well as the VC voltage. Okay, the collector and emitter voltage. So we'll draw this one, that one. If we go for this expression, we'll get VCC minus ICRC. So this current through the RC is what? IC current, and let me write here. So here the current is what? IB current. Base current, here the current is IC current. So VCC minus ICRC and here plus VCE equal to 0. VCC minus ICRL, RC resistor, ICRC minus VCE equal to 0. From this we will get what? Output expression, and we need the 2 points here. One point is A and one point is B. Please observe this. Okay, here we are writing the mathematical expression in the output port. Find out these points. The point of the DC load line on the x-axis, that is on the VC axis, as well as the point on the y-axis, that is on the IC axis. So here the points, if I take these points are A, this point is B, A point, B point. Then we can find out the A point. We can find out the A point. A point is on what? On the x-axis. So if we make VC values y value 0, then y means what here? IC. We keep IC equal 0, then we are going to get the point A. Similarly, if we want to find out the point B, we'll keep VC equal 0, then we are going to get the point IC value. This is a B point. Let's do that. So here, if I make IC value 0, for IC equal 0, let's make IC equal 0 on the above expression, then we'll get what? VCE will be, VCE will be what? VCC. That implies point A will be VCC comma 0. Similarly, if I keep VCE value 0, VCE equal 0, then we are going to get what? IC value as VCC by RC. You can observe here, to make VC value 0, they will get VCC minus IC RC equal 0. So then IC will be the VCC by RC, or we can take it like RC as a load or load express, whatever. From this we can take that point B. Point B will be obviously x value is 0, x coordinate is 0, and y coordinate is what? VCC by RC. There's 2 points, and the line joining points of the A and B is going to be from the DC load line. So this is the DC load line will be the line joining of A point and B point, A point and B point. So it is about finding the Q point, and if you find out this Q point on the middle of the this DC load line, so after doing the mathematical analysis, and if you get this point Q point on the middle of the DC load line, then we can say that the corresponding power amplifier is a class A power amplifier. Or else if we are not going to get on in the middle of the DC load line, then it is not class A power amplifier, right? So this is about finding the Q point and checking the Q point on the middle or not. So after that, let's do here we can write VCEQ will be what? VCC by 2. You can observe here. This point is what? This point is the VCEQ, and this point is the ACQ, and we got with these values, these two values. So there is we have to show this point. Yeah, yes. You know, observe here. What is the cube A point here? At this A, we are getting which value? VCC value. So here we are getting the value VCC, right? And here we are getting the value as ICC by RC. That's B value is what? ICC by RC. Okay. So you can observe here what is the VCQ is. VCQ is the middle of this Q point is the middle of the mid value of the in between this 0 and A. For example, we are having VCC is 10 volts, there is 5 volts, then we are going to get VCQ is what? 5 by 2 volts, right? That in the same manner, if you are having this value, this at B we are having the IC value is 5 milliampere, then we are going to get ICQ with the 5 by 2 milliampere, right? So because it is the on the middle of the Q point, so we are going to get half of those values. So we will get ICQ. We can write VCQ as VCC by 2 VCC by 2, and ICQ will be the ICC VCC by RC by 2, and these are the what? These are the Q points. These are the Q points, and these are the ideal values. Ideal for the class A power amplifier. Now let us see the power calculations. Let's see the power calculation for class A power amplifier. Find out the AC output power. Let's find out the AC output power. And you know that while we're finding the output powers in our power, in our electrical, we are having the formulas what? With respect to voltage and resistor, and there is a V square by R. And with respect to current and resistor, there is I square R. And in terms of voltage and current, VI, right? So here we're going to take among them whatever the formula should have goal. Here we are going to take the voltage. There is a V square by RL. There is a load resistance is RC. So here I will take RC as RL. So V square by RL, and we will take here RMS values. So while you're finding the AC power, we have to take the RMS value. So I'm going to write PAC. PAC will be the VO RMS square by RC. And if I take RC as load resistance, RC as load resistance here, RL is the RC, V square by V square RMS by RL. So here if you are having one waveform here like this, sine waveform, and this is the peak value, these are the peak to peak values, and for this waveform, what is the RMS value? Anybody can tell me? So we are having the sine waveform, and the peak to peak values are the VP and minus VP. And for this case, what is the RMS value for this waveform? Post your answer. RMS value of the sine waveform. And 707. The maximum value is VP, not 1. Maximum is not 1 volts. Here maximum values are taken VP. Okay, VP by root 2. Very good. So here, in the further, I'm going to write VRMS. VRMS is the maximum value. That is the VP. That's output VOP over root 2 by whole square by as usual load resistance. Here RMS value VO RMS equals to the maximum value peak value by root 2. Now here, what is the peak to peak voltage actually? Is the 2 times of peak value, right? So from this we can write peak value is what? Peak to peak by half of the peak to peak value. You can observe here. So this is the peak to peak. VP to minus VP is the peak to peak. We call peak to peak value. And this is the, if VP is 5 volts, then we can say peak to peak is how much? 10 volts, right? So same here, VP is the 2 times of VP. So we can write VP as the VPP by 2. So that's I'm doing here. So here in case of VOP, I'm writing the peak to peak value of voltage by 2 root 2 whole square over load resistance. So if we do the calculation, we are going to get peak to peak square by 8 times of RL. So this is the AC power output calculations here. So for ideally, if you do I'm writing one more, V maximum minus V minimum. There's a peak to peak value is what? V maximum minus V minimum whole square by 8 times of RL. I have written the peak to peak value is simply V maximum minus V minimum by this is the output AC power. Let's do this ideal calculations. So if I do the, if I find out the ideal output power, there's a maximum output power here for ideal, for ideal. So what is the V minimum value here? V minimum will be 0 and V maximum will be VCC. You can observe here. So here you can observe our V maximum will be the VCC, right? So this is the V maximum, VCC, and this is the V minimum, that's 0, ideal case. I'm talking about ideal case. So VCC is the maximum value, 0 is the minimum value. So why I have taken this one? If you want to find out the maximum output power, if you want to find out the maximum AC output power, then we'll take maximum values and minimum values here. So if I substitute this maximum values and minimum values in the above expression, we get from this we get maximum output power, maximum output AC output power, that will be given as PAC max will be given as, the substitute V max equals VCC and V minimum is 0. In this expression we'll get VCC minus 0 whole square, that is the VCC square, that is the VCC square over 8 RL. This is the maximum output AC power. So this is the maximum output AC power. Okay. So after that, let's find out the efficiency. The efficiency plays major role in our electrical. Why? Because whatever component we are going to design, as whatever equipment, whatever element you are going to take, we have to check for whether it is efficient or not. And you know that what is meant by efficient. Yes, no? So maximum output AC power. Okay. After that, if we want to find out the what efficiency, we required what output as well as the input, and we have find out the output expression is what PAC equal output AC power is what V square by 8RL, V square CC by 8RL. So if I want to find out the input power, here what while we are doing the DC analysis, so we are going to talk about the DC input power. So input DC power, if I write input DC power, input DC power and PDC will be given as, voltage into current. That is voltage is what output voltage is VCE, as will take VCC or maximum output voltage, and we're going to take the current passing through the transistor. And what is the current passing through the transistor in the during this what Q point section, it is ICQ. So this is a VCC into ICQ. That will be written as VCC into, and we know that ICQ is what? ICQ is the VCC by 2 RL. From this we can say that the DC output power, TDC, will be the VCC by to RL. And from this that implies efficiency. కొంచెం చెప్పాను నేను మీ లింక్ పంపాను గ్రూప్ చూడలే జూడ్ అయిపోయిందా ఎగ్జిక్యూట్ అయిపోయిందా that implies efficiency will be given by you know what is efficiency actually efficiency is the output over input that means how much input we are giving for a particular like circuit and what is the output you are getting so that is given by efficiency and if it is more efficient we are going to get what more than the one value which is not efficient will get less percentage like efficiency will be given by POAC output AC output power by this input DC power. Input DC power that is PAC by TDC. And we got PAC is what VCC square by 8 RL that we observed and PDC is V square CC by 2 RL. And if you do this cancellations of VCC as with RL, you're going to get the value as what? It's about 25%. We get is 1 by 4, that is 0.25, 0.25. That implies the efficiency is going to be what in terms of percentage? 0.25 into 100. So we're going to get 25% efficiency. It is the less efficient. So we're getting the less efficiency. We're getting the less efficiency for class A power ampere. It means what? 25% means what? If you are giving the DC input as 1 volt, for example, if you are giving input DC as 0.5 volts, 0.5 volts, then what about output here we're going to get? We're going to get AC output as 0.25 into 0.5. It's about 0. How much? 125, right? Is it? So here, if we are giving the PAC as 0.5 volts, we are going to get PAC as 0.125 volts. That is, we are not getting the uh, high output power here. We are not getting the more output power here. So it is the less efficient. This is class A power amplifier is the less efficient by. And if we talk about the advantages and disadvantages of this class A power amplifier, advantage is it's a simple circuit. We're having only a cell bias voltage device circuit, and the conduction angle is how much we have observed. The conduction angle is what? 360 degrees. We observe the 360 degrees as conduction angle. Let's write down here advantages. And disadvantages. Advantages and disadvantages. So here you can observe circuit diagram. There is a simple circuit. Simply we are using voltage divider. So it is a simple circuit. And we observe the what is the conduction angle actually. We are getting the complete cycle, right? We are getting the complete waveform, sine waveform, right? Nothing waveform is going to be clipped here. So it is a conduction angle is 360 degrees. That is, we are getting the full swing without clipping. We are getting the full swing waveform without any clippings. Now coming to disadvantages. So just we observe that it is a very poor efficient. It is having the less efficiency. It is a poor efficiency. Poor efficiency. This is a major disadvantage. As well as one more disadvantage is the circuit is going to be, we need a regular regulated power supply. So I hope you're going to see this word regulated power supply in the laboratory. Okay, and this is about the class A power amplifier. So what we observed here, we have observed the simple circuit diagram and this waveform and mathematical calculations. We have find out the efficiency. So by this, I am concluding today's session. So we'll discuss the our remaining class. There is remaining amplifiers, class B and class AB in the next class. So by that we are going to finish our third unit. So I am going to take next class on Saturday, that is Saturday afternoon. Okay, I will share the PDF. I will share the PDF. Don't worry. I'm going to take class on Saturday. Please keep your mind that. So please inform if anybody is asking you to take the class. Please tell him that there is